This is the second part of my discussion of the normal distribution. Let me now go back to my frequency example at the beginning of the lecture. If I transform each of the scores on this test or whatever it was into a z-score, this is what I get. Those who scored a 10 now have a z-score of negative 1.84. Those who scored a 20 have a z-score of negative 0.92. Those who scored 30 were at the mean, so their z-score is 0. Those who scored 40 have a z-score of 0.92, and those who scored 50 have a z-score of 1.84, or almost 2 standard deviations above the mean. And this is where each of the z-scores is under the curve. You'll notice that a z-score for those who scored 30 is right at the mean, and 40 and 20 go out almost a standard deviation, and 10 and 50 go out almost 2 standard deviations on either side of the mean. I'm going to use the table to look at the z-score for a raw score of 40. 40 transforms to a z-score of 0.92, or almost 1 standard deviation above the mean. I go down the z-score column to 0.92. There's the z-score for 40. The first useful bit of information from the table is how much area is between the mean and this z-score. In other words, what percent of scores is between this z-score and the mean? What percent goes from the mean over to this z-score? The chart tells me that it's 0.3214. It's called the area between the mean and this z-score, 0.3212. What it means is that there are an additional 32.2% of the scores between the mean and this z-score. We know that 50% of the scores are below the mean, so I add 32.12% to the 50%, and I find that 82.12% of the scores are at or below the z-score of 0.92. You will recall that this means a score of 40, which is a z-score of 0.92, is at the 82nd percentile. The table also gives me a shortcut to this information if I'm on the positive side of the mean for z-scores. It has a column for the area beyond the z-score. In this case, it is 0.1788, or 17.88%. If I subtract 17.88% from 100%, I obviously get 82.12% of the scores below that z-score of 0.92, or the 82nd percentile. So I hope this shows you the difference between those two columns. The first column is the area from the mean over to whatever z-score you're working with. The second column is the area out in the tails beyond the z-score that you're working with. I'm going to use the table to look at a z-score for a raw score of 20, which is a negative 0.92, or almost 1 standard deviation below the mean. Again, I go down to the z-score column to the 0.92 again, although this time I need to keep in mind that it's negative, so it's on the left-hand side of the mean. The area under the curve from the mean to the left to that z-score of 0.92 is 32.12%. We know that the percent of scores above the mean is 50%. So if we add 32% of the scores going down to the z-score of negative 0.92, we find that 82% of the scores are now above the z-score. In other words, for the students who scored 20 points, 82% of the students scored above them. Do you see how this is the reverse of the example I just gave for the positive z-score? These students are at the 18th percentile. 18% of the scores are below them. We can also get the percentile rank from the table. Remember that the percentile rank is the percent of scores below the one in question. The table tells us that the area beyond the z-scores, so that's going to be to the left in this case, is 17.88%. So it's the 18th percentile. I'm going to show a couple of examples of other ways to use the table. Suppose I have 500 scores on an exam, so my n is 500. The mean is 150 and the standard deviation is 13.2. I want to identify the potential students who are at the 35th percentile or below. I'm going to be concerned about those students because that's pretty low. I need to know what score will be my cutoff point, and I need to know how many students I need to be concerned about. 35th percentile is the score at which 35% of the scores are at or below. And I'm looking for something below the mean because it's which would be the 50th percentile. I look down the column that shows the area below the z-score or beyond the z-score. I look down that column and it's clear that the area at the 35th percentile, you can see the area is 0.3520. That's the area below or beyond where this score is a z-score of 0.38. I'm below the mean, so I know that that z-score is negative. How many scores am I going to be looking at? 35% of 500 is simply 165. Now I need to know my cutoff point in raw score terms. You will recall that you can transform a z-score to a raw score if you have the mean and standard deviation. I multiply the standard deviation by the z-score and then add it to the mean. So I find that a score of 144.98 or 145 is going to be my cutoff point. In other words, I'm concerned about the 165 students who scored 145 or below. This has been a lot of information about the normal distribution curve. I hope you have a conceptual understanding of this important tool. It was built on probabilities, and we want our data to approximate a normal distribution curve for most simple data analyses. It represents each vertical line represents one standard deviation from the mean or a z-score. And rather than doing all the math, we use a table when calculating. One last thing I didn't mention is that the table in your textbook gives you a column for the ordinate. We don't need to worry about that in this course.